Hey everyone, and welcome. Ever look at your phone or your laptop and just wonder how it all works? It seems crazy complex, right? But what if I told you that at its heart, it's all built from a really simple set of tools and parts? Today, we're going to open up that toolbox and see what's inside. But that brings up a huge question right away. Electricity is literally invisible. You can't see it. So how on earth do we know what's going on inside a circuit? How do we see it, measure it, and get it to do what we want? Well, that is exactly what our toolbox is for. So here's our game plan. First up, we'll check out the tools that let us see this invisible world. Then we'll make the basic building blocks. I like to call them the Legos of electronics. After that, we gotta learn the rules of the road, the laws that make sure everything plays nice together. And to wrap it all up, we'll see the stuff in action, turning the power from your wall into something your phone can actually use. All right, let's jump right in. First up, the gear that makes the invisible visible. To really work with electronics, you have to be able to measure what you can't see. And these tools, they basically give you superpowers. Okay, on the left, you've got the digital multimeter, or DMM for short. The best way to think of this is as the measuring tape of electronics. It gives you the hard numbers, voltage, current, resistance, super precise. And then on the right, you have the oscilloscope. Now, if the DMM is a measuring tape, the oscilloscope is like a super high-speed camera. It doesn't just give you a number, it gives you the whole picture of an electrical signal as it zips by. Let's zoom in on that DMM for a second. Its job is to measure those core properties: voltage, current, and resistance. It's the first thing you grab to get the basic facts. How much voltage are we dealing with? Is current actually flowing? It is, without a doubt, the Swiss Army knife for anyone tinkering with circuits. Absolutely essential. But this is where the oscilloscope just blows the multimeter out of the water. It shows you what the signal actually looks like. This beautiful flowing shape here, that's a sine wave. It's the classic waveform of the AC power that comes out of your wall. A multimeter would just give you a single number, like 120 volts. But the scope shows you its rhythm, its shape, its entire personality. Okay, so we've got our tools to see and measure. Now, what are we actually measuring? Let's meet the fundamental components. These are the electronic Legos that you can use to build just about anything. We'll kick things off with two of the most common parts you'll ever see. Over on the left is the resistor. And just like the name says, it resists the flow of electricity. Think of it like a narrow section in a pipe that limits how much water can get through. On the right, we have the capacitor. This little guy stores up energy, kind of like a tiny battery that can charge and discharge in a flash. It's like a small water tank that can fill up and then dump all its water out at once. And now for one of my favorite components, the diode. This thing is a game changer. Why? Because it acts like a one-way street for electricity. Current can flow one way, through the direction the triangle is pointing, but it gets completely blocked if it tries to go the other way, against that flat line. It is an electronic one-way valve, and that simple idea is incredibly powerful, as you're about to see. So, we have tools to see, and we have parts to build with. But how do they all fit together? You can't just throw them onto a board and hope for the best. Just like language needs grammar, electronics needs a few basic rules to give it structure. Our first rule is called Kirchhoff's current law, or KCL, and honestly, it's just common sense. All it says is that for any point in a circuit, whatever amount of current flows in has to be the exact same amount that flows out. You can't just lose current along the way, and you can't magically create it out of thin air. It has to go somewhere. And this picture shows it perfectly. Imagine that main current I is a river. When it hits that junction, it splits into three smaller streams. KCL just guarantees us that if you add up the flow of those three little streams, I1, I2, and I3, it'll be exactly equal to the flow of the big river coming in. Simple, right? What goes in must come out. This second rule is Kirchhoff's voltage law, or KVL. Now, this one is all about energy. It says that if you go in a complete circle, a closed loop, in a circuit, all the voltage you started with from the power source has to be used up by the components in that loop. Think of it like an energy budget. You get a certain amount to spend, and by the time you're back where you started, you spend it all. Take a look at this circuit. You've got your power source, Vs, pushing the current around. As it goes through each resistor, it loses some of that push. That's called a voltage drop, which we see here as V1 and V2. All KVL tells us is that the drop at V1 plus the drop at V2 has to equal the total voltage you started with from Vs. Every last bit of energy is accounted for. And hey, don't just take my word for it. Here's the proof. Someone actually built this circuit and took measurements. When they put in 10 volts, they measured a total drop of 10.27 volts. When they tried 5 volts, they got 5.10. I mean, come on, that is almost a perfect match. Those tiny little differences are just what happens in the real world with measurement tools. The bottom line is, these laws aren't just theory, they're how things actually work. Okay, this is the moment we've been waiting for. We've got our tools, we've got our Legos, and we've got our rulebook. So now, let's put it all together to solve a huge problem that exists inside almost every single electronic device you own. So the power coming out of your wall outlet is what we call alternating current, or AC. And as we saw on the scope, it's wild. It swings from positive to negative and back again 60 times every second. That's just chaos for sensitive electronics. Your phone, your computer, they need a steady, calm, one-way flow. They need direct current, or DC. So how do we tame that wild AC? Well, remember our hero, the diode? That one-way valve? This is its moment to shine. We put it in the circuit, and it lets the positive part of the wave go right on through. But when the negative part comes along, the diode slams the door shut. And just like that, look what we're left with. Only the positive bumps. We've just turned AC into a rough, pulsating DC. So let's just trace that path one more time. Step 1, you have that messy AC signal coming in. Step 2, our diode acts like a bouncer at a club, only letting the positive vibes in. Step 3, the result is this bumpy road of positive-only pulses. Now, it's not smooth DC yet, but this is the absolute crucial first step inside every single power adapter you've ever plugged into a wall. And there you have it. That's the basic toolbox of electronics. We have tools like the multimeter and oscilloscope to let us see. We've got our core building blocks, our resistors, capacitors, and diodes. We have the rules of the road, Kirchhoff's laws, that tell us how everything will behave. And with just those few simple concepts, we can do something as essential as converting power to run our entire digital world. It's kind of mind-blowing when you think about it. Every single piece of amazing technology we use is built on these simple, elegant, and really powerful ideas. They are the foundation of everything. So the real question is, now that you've had a peek inside the toolbox, what are you going to build with it?